Well, we got ourselves a big one here today. Improper integrals have been our Achilles heel of late, so we're going to try to tidy this topic up a little bit. The key here is this first sentence says, we are attempting to find the area of a what? Of an unbounded region. And right there, that sentence right there kind of contradicts normal logic. It says that you would think if the region was unbounded, then the area would automatically be infinite. But it's similar to the series. Like we've seen series that converge. You know, there's an infinite number of terms. We add them all up, and we actually come up with a finite answer. And it's the same idea with these series. Now I posed two here in these pictures. This first one is the integral from, switch up the colors a little bit, is the integral from 1 to infinity of 1 over x. And the second one is the integral from 0 to infinity. And the key that they have in common is that the upper bound on both of these is infinity. And both the graphs are asymptotic to the x-axis. So you'd think we'd get, logically, you'd think we'd get the same result. But what you'll notice here is the first one actually diverges, whereas the second one actually converges. And it has to do with the rate at which these graphs are approaching the asymptote, which in this case is the x-axis. The first one, it's approaching the x-axis, but at a turtle speed, and there's just too big of a gap in here as we go towards infinity. Whereas this next one, it gets on top of that x-axis very, very quickly. The space in between becomes minuscule, and therefore the ultimate cumulative area converges to a finite number. Now, our improper integrals come in a variety of forms. This first one up here in the upper left-hand corner, the upper bound is infinity, and I think that's the most logical one, and that's the easiest one to spot. As soon as we see that infinity sign, our brain automatically clicks and goes, oh, improper integral, we rewrite it in terms of a limit, we're good to go. The ones that get a little sketchy are ones like 2 and 3 here. Number 2, both the bounds are finite. You got a lower bound of 0 and upper bound of 1. Our brain doesn't automatically register improper right off the bat. We have to imagine what this graph looks like. We have to recognize that there's a vertical asymptote at x equals 0 on the left edge here. And because of this discontinuity over here on the left edge and the unbounded region at the top, I like to call it a leak. There's like kind of a hole in the graph. There's a leak. And because of that idea, we have to rewrite it as terms of a one-sided limit. And then the third idea, and these are the most tedious as far as work goes, is instead of having a discontinuity at one of the endpoints, we might have what we call an interior discontinuity. So this one here in blue, it might start off as the integral from -1 to 1, but then we would have to rewrite it in terms of two integrals. We'd have to go from -1 to 0, plus the integral from 0 to 1, and we'd have to write both of them in terms of a one-sided limit, and then what we could do is we'd have to solve both of them. If just one of them diverges, then the sum of the two also diverges. Now you also notice this one we could cheat a little bit because of the symmetry on this third one. We could just do the integral from 0 to 1 and then double that answer. Here's two really simple sentences that I want to get in our notebook, but it's the foundation of really being solid at these. And basically we're going to say the indefinite integral is convergent as long as when you take the limit, okay, and that's what they all have in common. We're going to rewrite every single one in terms of a limit. If you take that limit, the answer exists. Okay, in other words, and what makes a limit existent? Well, you get a finite number for your answer, basically. That's how you know if it exists or not. Now, on the contrary, if the limit does not exist, you get an undefined or you get an infinity, you know, some kind of non-finite answer, then the integral is said to diverge. And that's the lingo we're going to use throughout this lesson. So ultimately, at the end of the day, what's the biggest key to being successful at improper integrals? I'm going to boil it down to this one thing. Recognition. If we can look at the problem and recognize that it is an improper integral, then we're going to be pretty good at these. Half the battle is recognition. Half the time we don't even recognize we're tackling an improper integral, and that causes all sorts of problems. You know, when does that come into play? Well, think about this problem. You know, what if I was integrating 1 over x minus 1, and the bounds were, 0 to 3, okay? At first glance, there's nothing about this that screams improper, per se. Both bounds are finite numbers. 0 is finite, 3 is finite. But what we have to recognize is this graph, as we graph it, has a vertical asymptote at x equals 1. And then we've got a horizontal asymptote at y equals 0, which is not a big deal. But the graph sits down here, and then it sits up here. And so recognizing the existence of that vertical asymptote is we're going to rewrite an integral from 0 to 1, yada yada, plus the integral from 1 to 3, and then tackle both of those. Well, I've imported two AP questions that I think it possesses all the characteristics of an improper integral plus a little extra, kind of puts it in a slightly different context than what we're used to. And so we see here in our first question, we are combining two very key elements here. We're going to do the volume of a known cross-section, and in that meantime, we're going to be also identifying and tackling an improper integral. So here we go. We've got a certain solid, and the region's bounded by the coordinate axes. So we've got, whoops, grab the pen. Here we go. All right, rookie mistake. So there's your coordinate axes. Those are bounds. We also have the line x equals 16, which is way over here, we'll say. And then we have the graph of y equals x to the negative 1/4 power. Now, what does that really look like? That's, think of it this way, 1 over the 4th root of x, which behaves very similarly to like 1 over radical x. It's in that p-series family, asymptotic to not only the y-axis but also the x-axis, which makes this one doubly interesting. Now, for each solid, the cross-section is perpendicular to the x-axis. So here's my cross-section perpendicular to the x-axis. It forms the base of a square. So the length of that slice right there is the base of my square, which is then popping out of the paper at me. And they want to find the volume of the solid. Now, the key here is, because we're bounded on this left edge by the y-axis, we do have an improper integral. We've got a leak there on the left edge. And so here's how I'm going to set my, first things first, I got to do a little bit of slice analysis here. So my base is going to be 1 over the 4th root of x. My height of each slice is going to be the same because it's a square. The area of each slice is going to be base times height, which in this case would be 1 over radical x. And then the volume, here we go, is going to be 1 over radical x dx, and the bounds are going to go from 0 to 16. Alright, now because we have a discontinuity on the left edge, we're going to rewrite this as in terms of a limit. So we've got, let's see, volume is really the integral from a to 16. Now how would you define a? It's going to be a one-sided limit. It's going to be the limit as a approaches 0 from which side? Well, the region that we just shaded in sits to the right of 0, so we're going to say a is approaching 0 from the right side. Alright, let's see, how does that then look? We've got the limit as a approaches 0 from the right side. Now my antiderivative, and you can rewrite this as x to the negative 1/2 if you want and then integrate it. My antiderivative is going to be x to the positive 1/2 times a coefficient of 2. I think getting that 2 in there is maybe one of the bigger obstacles we've got. Don't forget about the 2. And we're going to continue to rewrite this in terms of a limit until I get to the evaluation phase. If I plug in a 16, I get an 8 minus 2 times radical a. Now we're ready for the evaluation phase. What's happening to that second term? Let's see. I'm getting 8 minus... Now, as a approaches 0, the value of radical a is also approaching 0. And so we end up with an 8. We've got a finite number. Not only does it converge, but it converges to a volume of 8. We've got just one more question here today. And I want you to, when you read this question, kind of sit back and admire the creativity of the question writers here. I thought this was a great question to test our knowledge on improper integrals and without it being the normal mundane approach. So they've given us this curve, k over radical x. K is an unknown constant. And they've defined two different integrals here. The first one is L, and the second one here is M. And they want to know which of the following statements is true. Is L smaller than M? Is L equal to M? Is L greater than M? Or do we not really know the values of L and M because of the fact we don't know K? That's the final question. So anyway, I'm going to tackle these one at a time. I'm going to jump on L first. And first thing I'm going to do is, because there is an unbounded edge here on the left side, let's see, we're going to rewrite this as the limit as a approaches 0 from the right side again, because the region that I'm investigating sits to the right side of 0. Integral from a to 1 of k times x to the negative 1/2. I think it's helpful if we rewrite it in that form so that we can ready to integrate it. Let's see, what's the antiderivative going to be? I'm going to add 1 to my exponent, and I'm going to multiply by the reciprocal of that new exponent. So my coefficient is ultimately 2k. Alright, if I plug a 1 in, let's see, what do we got here? Still need the limit, so I have not evaluated it yet. If I plug a 1 in, I got 2k minus 2k radical a. So what happens as a gets closer to 0, that second term, the value of radical a becomes 0 and gives me this. So what we're going to say is that k is obviously a constant, so we get a finite number. We're going to say that that first integral converges to a finite value of 2k. Now let's go attack the second one. I'm going to see if I can fit it in here side by side. What's m going to be? I think this is the easier one to spot. We're going to go integral from 1 to b, where b is the limit as b approaches infinity of k times x to the negative 1/2 power. Let's see. My limit as b approaches infinity, antiderivative is going to be 2k x to the 1/2 again, bounds of 1 to b. Going to rewrite that limit one more time. Be very diligent with your notation. These have started to be free response questions more so than multiple choice of late. So we've got 2 times k times radical b minus 2k. Now that first term, look at that first term. The value of radical b is approaching infinity, so 2 times that times k, whatever, that gives me infinity minus 2k, which is, we would say, a divergent answer, because infinity minus a constant is still infinity. Now let's compare these. What did we say? L turned out to be, let's see, we said L was 2k, and we said m was ultimately infinity. So what I'm going to do is I'm going to go with choice A. I'm going to say L is smaller than m, because L's finite and m's infinite. So that's the one that I fell in love with. So hopefully you feel a little bit better. Tomorrow we're really going to hammer our notation and just being spot on with these. And perhaps the greatest challenge, besides just recognizing them, is evaluating our limits. So it's going to be great review along the way. We'll see you tomorrow.